everyone. Welcome back to lecture series on aerospace propulsion. So, in the previous lecture, we were basically discussing about the brief introduction to what is this aerospace propulsion is all about, and then we have seen the basic classification of aerospace propulsion system, and then we have seen the one of the propulsion system, that is air breathing propulsion system, gas turbine. What is the operating principle of gas turbine, and what, based on what principle this gas turbine is working and all, we have discussed in the previous class. Okay, so in today's class, what we are going to see is that we are going to see the classification of jet engines. Basically, what are all the different types of gas turbines as well as other jet engine we utilize in the aircraft industry. That is what we are going to discuss in the today's class. So as a part of that, we are going to see only 4 types of gas turbines. Okay, that is Turboprof, Turbojet, Turbofan and Turboshaft engines in this particular lecture. Okay, so as we already know that what are the different types of gas turbines are. Basically, gas turbine we can classify into 4 types: turbojet, a turboprop, turbofan and turboshaft. This ramjet and scramjet, they won't come under the gas turbines. They are a bit different compared to that of the gas turbine. So that we are going to discuss in the next lecture. So as far as this lecture concerned, we are going to discuss only these 4 types of gas turbine engines. Okay. So in this 4 types of gas turbine engine, so as we already discussed, any type of gas turbine engine we take, we will have 3 major components which will present in the all type of gas turbine. Basically, that is compressor, combustion chamber and turbine. Okay, so this compressor, combustion chamber and turbine. Okay, so basically these 3 are what we call it as the gas generator. Okay, so with this gas generator, if I'm going to connect the gearbox and propeller, and if I'm going to connect one propelling nozzle, that is going to give me a turboprop engine. Okay, that is by connecting a propeller along with the gearbox and the propelling nozzle to the gas generator, we will get the turboprop engine. Okay, so how does this turboprop engine produces thrust, and what are the function of these individual component? That is function of compressor we know, and combustion chamber we know, and the turbine also we know. Okay, so other than that, what is the function of this exhaust nozzle and what is the function of this propeller? How does this particular turboprop engine, okay, is able to produce thrust force or shaft power or propelling power to move an aircraft? That's what we are going to see now. Okay, so this is an actual turboprop engine. Okay, so how exactly this turboprop engine is able to produce thrust is that, see, as you can see here in this, see, we have the compressor to increase the pressure, and we have the turbine, that is to extract some portion of energy from your fluid to rotate the compressor. Okay, and here we will have 2 concentric shaft. Okay, so one shaft will rotate the compressor. Okay, that is a set of turbine blades will be connected to the compressor, and set of turbine blades will be connected to the shaft. Okay, so you could say that portion of your power extracted from it, your turbine is used to rotate the compressor. Remaining portion is used to rotate the shaft. So the shaft is connected to the gearbox, and along with the gearbox we have connected the propeller. Okay, so what is the purpose of this propeller is that by rotating this shaft, we are able to rotate the propeller. By rotating this propeller, we are able to produce the forward force. That forward force, what we call it as the thrust force. Okay, so you could say that this how exactly this propeller is producing the forward force is it's similar to that of your airfoil. Okay, so we know that an airflow is passing over an airfoil. What happens? We have high pressure at the bottom, low pressure at the top, so which will result in an upward force. That upward force, what we call it as the lift force. Similarly, here a propeller also made of your airfoil blades. Okay, airfoil cross section. So when the flow is passing through the propeller, what happens is that when the propeller is rotating at high speed, okay, it creates the suction. So because of this section, what happens? Your local flow will tend to accelerate. See, your atmospheric air is still. When we are rotating the propeller, what is going to happen? It is going to attract the flow from the surrounding. So when it is attracting the flow from the surrounding, what happens is that when it is moving towards this location, okay, your flow will be accelerated. Okay, when the flow is accelerated in front of your propeller means, what does that mean? Acceleration means, when the velocity is increased, your pressure will be decreased. So because of this acceleration, what happens? There is a low pressure zone is created. Okay, and when the flow is passing through this fan, what happened is that, your fan is rotating, that propeller is rotating at high speed. It is going to exchange some of its momentum to the incoming fluid. So because of this exchange of momentum to your fluid, what will happen? Your flow will be accelerated when it is coming behind. Okay, so here if you look into that, in terms of velocity point of view, at the exit of your propeller, the velocity will be more. So as such, what happens? We are having a gaining in momentum when the flow is passing through the propeller. At the same time, after some time, what is going to happen? That accelerated flow is going to come to the rest, that is, it will attain equilibrium with the surrounding. So because of the deceleration, the pressure at the behind of your propeller is going to be increased. So we have a low pressure here and high pressure here. So because of that, what is going to happen? There is going to be a force in this direction. This force, what we call it as the thrust force. Okay, or you could say that, you see here, by rotating the propeller, we are creating the low pressure. Because of this low pressure, your object is trying to move in the forward direction. So that is how your propeller is able to produce the thrust force. Okay, that is the concept of your propeller, is that it is to accelerate the huge amount of mass flow into a less velocity. Okay, so anyway, we are going to derive the thrust equation later, but a simple thrust equation is that m dot a into ue minus ua. So you could say this is the ideal thrust equation. Okay, so this is the exit velocity, this is the inlet velocity of your flow, and this is the mass flow rate. Okay, so what happens in case of your propeller, that is turboprop engine or propeller aircraft, is that here we have a huge amount of mass, that is, we suck in large amount of mass from the surrounding. Okay, and accelerate to very low speed. So if there is no acceleration, suppose both velocity are same, means you won't have any thrust force at all. If you want to have a thrust force, there should be a difference in velocity or difference in momentum. Okay, so the main thrust contributor in the turboprop is basically mass flow rate. Okay, so that is why the basic principle in the propeller or turboprop aircraft is that huge amount of mass flow rate will be accelerated to very low velocity. Okay, so that's how your turboprop is able to produce the thrust force. Okay, so for what application we use this turboprop engine and what are the limitations of this turboprop engine is that, you see here, if you take the turboprop engine, almost 90% of your thrust is produced by the propeller, and 10%, only 10% is produced by the nozzle which is connected at the exit. So how does your nozzle, once again, it is able to produce the thrust is that same as here, your flow which is coming out of your turbine, it will be accelerated to some high velocity when it is passing through the nozzle. You know what is nozzle, right? It is a passage which will accelerate your flow. So when there is an acceleration, means your velocity or momentum of your flow is increased. So the difference in momentum at the front of your engine and back of your engine will result in one portion of thrust, that is the thrust due to flow coming out of your nozzle. So that contribution is hardly 10%. So you could say 90% of thrust is produced by the propeller alone. Okay, and where do we use, for what type of application we use is that up to Mach number 0.6 we use the turboprop engines. Okay, so what happens if we cross more than 0.6 or 0.7 is that, as you can see here, see at the root and the tip, when the propeller is start rotating, what is going to happen? At the root of your propeller, your RPM will be less. At the tip of your propeller, your RPM is going to be more. So as such, when the flow is passing through, what is going to happen is that here your flow may be subsonic, but when it reaches the tip of your propeller blade, it may reach the sonic value. So when there is a sonic flow, in a supersonic flow, there is going to be a formation of shock wave. So when the propeller RPM is increased beyond certain limit, that is, if the tip of your blade reaches the sonic speed, there is going to be a formation of shock wave. That shock wave will result in structural damage to your propeller. At the same time, because of shock, you will have more amount of loss. Okay, so that is why because of this loss, what happens when you operate your propeller aircraft more than 0.6 Mach number, its efficiency will come down. That's why these turboprops are used only for aircraft which is having a speed of maximum up to 0.6 Mach number. Okay, now we have one more type of gas turbine which we call it as the turbo shaft engine. So what is the difference between this turboprop and turbo shaft? Is that basically both are almost similar. You could say that the operating principle of the turbo and turbo shaft both are same, and both the engines, both turboprop and turbo shaft, they produce most of the shaft power. Only difference is that turboprop we use for the aircraft application, whereas for turbo shaft we use for the helicopters. Okay, see, as you can see here, we have the intake and we have the compressor, combustion chamber, and the compressor. We have something called power turbine or free turbine. Okay, this power turbine or free turbine is the one, okay, which is going to produce almost whatever the remaining energy available in your flow when it is passing through this compressor turbine. So why do we call it as a compressor turbine? Is that because this particular turbine is to power the compressor, okay, and this power turbine is to rotate the rotor blade of your helicopter. Okay, so same, both your turboprop and turbo shaft, the ultimate outcome of this is basically a shaft power. In aircraft, in turboprop we use the shaft power to rotate the propeller, whereas in the turbo shaft we use the shaft power to rotate the rotor blade of our helicopter. Okay, so our next major type of your gas turbine engine is a turbojet engine. Okay, so nowadays most of the fighter aircraft which utilizes this turbojet engine. So what are the basic component of this turbojet engine other than the gas generator, which is basically compressor, combustion chamber, and turbine? They are air intake and nozzle. Okay, that is, if I'm going to connect a intake and a nozzle to the gas generator, it is going to give me a turbojet engine. Okay, so how does this turbojet engine produces the thrust force or propelling force to operate the aircraft? Is that in turboprop we have seen large amount of mass flow rate is accelerated to less velocity. So there the mass flow rate of your air plays a major role in production of thrust, whereas in the turbojet engine we accelerate a less amount of mass of air to very high velocity. Okay, so here once again this T is equal to m dot A into UE minus UA, this ideal equation. Okay, so in this UE minus UA plays major role in case of turbojet engine. Okay, so that is, this is less and this is very high. Okay, whereas in turboprop mass flow rate is high and your velocity difference is less. Okay, so now we are going to see what is the function of this each individual component. Okay, so first we have the air intake. Okay, so what will be the shape of your air intake? Will be kind of a divergent duct. Okay, so what is the purpose of this divergent duct? Is that it is to decelerate the incoming flow. Okay, so for example, say my aircraft may fly Mach number more than 1 or near to Mach number 2. What is the function of this intake? Whatever the inlet Mach number may be, it is to decelerate your Mach number to close to 0.5 to 0.6. Okay, when it is enters the compressor. Okay, irrespective of engine, what is the function of your intake? Is that it is to decelerate the incoming flow to Mach number required for the compressor intake. Okay, so why do we need to reduce the Mach number to this range of 0.5 to 0.6? That once again, you see, when the flow is passing through the compressor, what we are doing, we are basically increasing the pressure. Okay, so how do we increase the pressure across the compressor is that we have something called a rotor blade and stator blade in the compressor. In the rotor blade, we exchange the or we increase the momentum of our incoming flow, and in the stator blades, we decrease, that is, we convert the whatever the momentum increase to the flow to the pressure. So by that, by slowly having multiple stages, what is a stage means basically a set of compressor, rotor blade and stator blade, what we call it as the stage. Okay, so as it passing through the number of stages, your pressure is going to keep on increase. So if I'm going to send my flow directly at Mach number more than 1, what is going to happen? There is going to be a formation of shock wave in the compressor, which will lead to too much amount of loss. So we don't want that. So in order to reduce the shock loss in the compressor, we decelerate our flow to Mach number range of 0.5 to 0.6. Okay. So once this flow pressure is increased across your compressor up to certain limit, say it can go up to 30 times of your atmospheric pressure. Okay, so when the high pressure flow is coming to the combustion chamber, there we will spray the fuel and do the combustion. Okay, so by doing the combustion, what I am doing, I am increasing the total temperature of my flow. Okay, so here inside your combustion chamber, what we do is that here your Mach number may be close to 0.8 or 0.7. When we send our flow to the combustion chamber, once again we will decrease the flow Mach number 2 in the range of 0.2 to 0.3. Why do we need to reduce this Mach number to 0.2 to 0.3 is that if I go beyond that, we won't have the stable combustion. So stable combustion will occur at the range of 0.2 to 0.3. So we have to decelerate our flow to the 0.2 to 0.3 Mach number range. So there we will do the combustion, and that high pressure and high temperature flow will pass through the turbine. When it is passing through the turbine, it is going to produce the shaft power. That shaft power will be utilized to rotate the compressor. Remaining flow, that is flow which is having certain amount of thermal energy, when it is passing through the nozzle, it is going to produce high velocity exhaust stream. Okay, so this high velocity exhaust stream, basically it will have velocity very high compared to the top inlet velocity. So basically here my UA, here it is UE, my UA is less, my UE is very high. I'm creating the momentum difference. Okay, so by creating the momentum difference, I'm able to produce the thrust force. Okay, that is how your turbojet is able to produce the thrust force. Okay, so next type of engine we are going to see is something called a turbofan engine. Okay, so you could say this turbofan engine is basically, it is a combination of a turboprop engine and turbojet engine. Okay, so why do we need this turbofan engine is that you see the efficiency of your turboprop stops at 0.6, and your efficiency of your turbojet, it is better in the supersonic regime. So in between that 0.6 to 1, okay, so most of our commercial aircraft flies. Okay, we need an efficient engine. Efficient engine is that basically which utilizes less amount of fuel to produce more amount of thrust. Okay, so what they have done is that they have combined the concept of turboprop and turbojet. Okay, in order to produce the thrust force, that type of engine, what we call it as the turbofan engine. Okay, so as you can see here, this portion is basically, it is a turbojet, and this portion is a turbofan concept. See, instead of keeping a fan outside, we'll keep the fan inside the duct. So we call this as the ducted fan. Okay, so here we have a core engine. Okay, the function of this core engine is to produce the shaft power to rotate the compressor as well as to rotate this fan. Okay, so what we do is that by rotating this fan at high speed, we will be able to accelerate a huge amount of mass flow through the bypass of your core jet. Okay, and this jet also is going to produce certain amount of thrust. And here, this thrust concept is basically similar to that of turbojet, and the thrust produced by the fan is similar to that of your turboprop. So by combining these two together, they are able to make an efficient engine which is having better efficiency in the range of 0.6 to 0.8. Okay, which is the Mach number range of the nowadays modern commercial aircraft. If you look at the almost all the commercial aircraft nowadays, they utilize this turbofan. Okay, so this force and what we call it as the core. Okay, so and sometimes we call this turbofan as bypass engine. Okay, bypass engine. Why do we call it as a bypass engine? Is because center portion we have a core flow, right, and surrounding also we will have a cold flow which is passing through without doing a combustion. Okay, so the center flow we call it as the hot flow, or the surrounding flow we call it as the cold flow. So what is this bypass ratio? Based on this bypass ratio, we have a low bypass, medium bypass, high bypass ratio, turbofan engine. So what is the bypass ratio? Is basically it's the ratio between mass flow rate through the bypass divided by the mass flow rate through the core engine. See here also certain amount of airflow will be entering, and surrounding your engine also certain amount of mass flow rate will be entering. So that m dot cold flow divided by m dot hot flow, what we call it as the bypass ratio BPR. Okay, so based on the bypass ratio, okay, we will have, that's what I already mentioned, a low bypass, medium bypass, high bypass engine. So most of our commercial aircraft, they utilize the high bypass engines. Okay, so till now we were discussing about 4 types of gas turbine engines. So we started off with the turboprof. Okay, and what is the concept of turboprof? That is acceleration of huge amount of mass flow rate to low amount of velocity, whereas in the turbojet, acceleration of small amount of mass flow rate to very high velocity, whereas in the turbofan, it is a combination of both. In the bypass, a large amount of mass flow rate is accelerated to less velocity. In the core section, less amount of mass flow rate is accelerated to very high velocity. So by combining that, we are able to get an efficient engine which is able to operate in the Mach number range of 0.6 to 0.8, in which the zone where either your turbojet or your turboprop are efficient. By combining these two concepts together, we are able to get one engine. This engine what we use in the almost all the commercial aircraft. Okay, so with this I'll finish today's lecture. Okay, so in next lecture we are going to discuss about the another bit of completely different type of jet engine. Basically they are a ramjet and scramjet engine. We are going to discuss in the next class. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.